Our second unit in coordinate geometry deals with distance and midpoint, both of which are topics we've previously discussed. If you see the learning targets, I can use midpoint and distance formulas to find missing coordinates and figures. I can use midpoint and distance to verify geometric figures. I can use midpoint and distance to calculate perimeter and area. So we're going to be using midpoint and distance to do these three things: find missing coordinates, verify geometric figures of their properties, and calculate perimeter and area. We'll also be venturing into some three-dimensional pieces here. I can calculate three-dimensional distances, and then I can calculate the point that is a fractional part of the way between 2 points. That's a second new idea. So let's review some formulas. We know the midpoint formula. You take the two x coordinates and you average them, and then you take the two y coordinates and you average them to get your midpoint if the points are x1, y1, and x2, y2. Similarly, to find the distance in 2 dimensions between those 2 points, you have seen this before. We subtract the distances, so x1 minus x2 quantity squared plus y1 minus y2 quantity squared. Does not matter which order you subtract them in, you are squaring, so the sign issues will disappear. Again, that would be for points x1, y1 and x2, y2. If we're going to calculate distance in 3 dimensions, we would of course have coordinates that have 3 points, x1, y1, z1, and x2, y2, z2. And the distance formula just simply adds one more piece on. So it looks exactly like what we had above, but now in addition we have to subtract the z coordinates and square them. All right, and you'll see how we use that in a minute. Division of a line segment. So what this is talking about, if we have some point x1, y1, and we have another point x2, y2, and we have the segment, and we want to know a fraction of the distance down. So this represents some fraction of the distance, and we want to know where is this point. All right, to do that, we take, for x, the starting value, x1, so I'm going to put here starting x value, and to that we add f, which represents the fraction of the distance, and then we want the x distance, which is represented by x2 minus x1. So this right here represents the distance between the x values. And we are taking a fraction of that distance and adding it on to the first x value. So similarly, y, the y value, would be the starting y value plus the fraction of the y distance. Important to note, when we're calculating that y distance, it's the second coordinate minus the first coordinate. If we were going to take a fraction of the distance starting at this point, moving in this direction, I would have to begin with x2 and I would have to begin with y2. So these definitely have to be your starting values, whichever point you're leaving from. You'll see how that works in a minute. Let's take a look at the examples. A segment has one endpoint of -7,9 and a midpoint of 4,2. Calculate the coordinates of the other endpoint. So let's remind ourselves. Here's the midpoint formula. But now I know the midpoint. I have that. So I know this right here should equal 4. And I know the y value should equal -2. I also know one of the points. So I can say 4 equals, for x1, I can use -7. I'm missing the other value. To finish calculating that, I multiply both sides by 2. And then if I add 7 over, I get x2 to be 15. I can do the same thing for y. This value has to be the y value of the midpoint, which is -2. I know one of the y values is -9. I'm missing the other y value. So if I multiply by 2, I get -4 equals -9 plus y2. If I add 9 to the other side, I get y2 to be 5. So my other endpoint would have coordinates 15, 5. Don't forget, you could always plug that in. It's a quick way to check your answer if you wanted to do that. All right, example 2, a parallelogram has these vertices. So I'm going to make a little sketch here. 8, 10. 2, 10. Well, let's make this 2, 10. That does not look like 8, 10. So let's go 2, 10. Let's go 8, 10. And let's go 6, 3. Right about here. Okay. Now the trick on this one is notice the points are not labeled, so I don't exactly know how to connect these. So the first one I'm kind of looking at, I see this parallelogram somewhere right here. I'm not sure exactly where. I'm looking for this point. Well, I'm going to use that idea that we talked about in the last section about slope, right? I know these lines are parallel. So my slope, I'm looking at 10 and 3. So to get from 10 to 3, I went down 7. And then I'm using my x coordinates, 8 and 6. I'm at 8 and I come back to 6. So that's -2. So now on the same regard, I'm going to look here. I have to go from 10, I have to go down 7. So that's going to put me, now it's the y coordinate, I'm not going to mess this up this time. If I'm at 10 and I go down 7, I'm going to be at 3. And now I have to move 2 to the left here. All right, so this was down 7. This is 2 to the left. Look at your x coordinate. You were at 2. If you're at 2 and you go 2 to the left, you should be at 0. So one option is 0, 3. Let's keep a list of that right there, 0, 3. I'm thinking that some of you might have looked at this picture a little differently. So if I sketch it again, 2, 10, 8, 10, let's put 6, 3 right here. If I would have connected them in a different way, perhaps like this, right, you might have pictured the parallelogram going in this direction, which is absolutely a possibility. So now I'm looking for this point right here. So I'm going to use the pattern again on the two sides, but now this time it's the left side where I know the pattern. I'm up at 10. I'm going down to 3, so that's still down 7. Now I'm at 2, and I'm moving over to 6. From 2 to 6, that is moving 4 to the right. So now I'm going to do the same pattern. I'm going to go down 7. Remember, that's coming off the 10. That's the y value. So if I'm at 10 and I go down 7, that's a y value of 3. Then I have to go to the right 4. Remember, I was starting at 8. So if I'm at 8 and I go to the right 4, 8 plus 4 puts me at 12. So there's a second possibility, 12, 3. Let's look at one more diagram. See if anybody thought of it this way. 2, 10, 8, 10, and 6, 3. Look at the previous ways we've connected them. We connected them in this direction. We connected them in this direction. How about we try this direction? This is usually the one I think that students don't picture as much. Couldn't we also have a parallelogram that looked something like that? So I'd be looking for these points right here. So now I think what I'm going to do is I'm going to look. I know this side should be parallel to this side, for example. So I'm going to look at the relationship to get from 6, 3 to 8, 10. I know that should be the same as the pattern to get from 2, 10 to this point. So if I look at my rise, I'm looking at my y values. I was at 3, I'm moving to 10, that is up 7. And now I look at my run, I was at 6, I'm moving over to 8, that's right 2. So let's do that again. I'm going to rise. I'm working off of the 10, so if I'm at 10 and I have to rise 7, that puts me at 17. I went a little too high there. Now if I have to go over, I have to go over 2. I'm looking at the x coordinate, which was 2. I have to be at 2, move 2 to the right, that puts me at 4. So my other option here is 4, 17. So those are my 3 possibilities. Okay. All right. Example 2. And yes, by the way, you do have to list all. So one answer will not be enough. Example number 3 here under Roman numeral 2, use midpoint and distance to verify geometric figures. We did a little bit of this in the last section too. We're showing that the adjacent sides of a kite are congruent. So again, I'm just going to make a really quick sketch. 310, that might be up here. B is 615. 615, that's B. C is 910, so maybe out here. And then D is at 62. So hopefully you can see we have a kite-shaped figure here. A sketch tells me which sides I know I want to be congruent, so I'm going to use the distance formula to show that sides are congruent. So I'm going to start with the distance of AB. Using my distance formula, I can see A here and B right above. I'm going to do x minus x quantity squared plus y minus y quantity squared. That's going to be the square root of -3 squared is 9, -5 squared is 25, so that's going to come out to be the square root of 34. I know that piece should be congruent to BC, so I'm going to look at that one next. BC are these 2 points, so if I do x minus x quantity squared plus y minus y quantity squared. 6 minus 9 is -3, squared is 9. 15 minus 10 is 5, squared is 25, which is the square root of 34, so I can see those indeed are congruent. Next, I'll check the bottom 2. I'm going to start with AD. It's just a lot of distance formula calculation. That's the first one here and the last one. So I'm going to do x3 minus x6 quantity squared plus the y's 10 minus 2 quantity squared. That will be -3 squared is 9, 8 squared is 64. So that will be the square root of 73. I know AD should match CD. Make sure you're looking carefully at your segments and you're not accidentally calculating diagonals. So DC are these last 2 points. So x minus x quantity squared, y minus y quantity squared leaves me with 3 squared, which is 9. 10 minus 2 is 8 squared is 64, which is also the square root of 73, and we have congruence. So I showed that adjacent sides were congruent. Example 4 here, using midpoint and distance to calculate perimeter and areas of figures. All right, it says find the area of the parallelogram with the following vertices. I'm going to label these just so when I sketch my diagram I can talk about them. Looks like this is kind of going to be in the 4th quadrant mostly. -3, 2, that would be up here. 6, 2 might be out here. Hopefully you can see that is a horizontal line. 14, -13 is going to be, wow, down here somewhere. Am I still on the screen here? 14, -13. And then 5, -13 would be somewhere back here. Trying to make it look like a parallelogram. Okay. It wants the area, so now you've got to dig back to chapter 11. The area of a parallelogram is the base of the parallelogram times the height of the parallelogram. So if I worry about the base first, that would be this segment right here. That is a horizontal segment, so I'd be looking at the 5 and the 14. We've made these calculations before. Remember, it's right minus left. So I would do 14 minus 5. That makes that equal to 9 for my base. Now the height, remember, has to be the perpendicular distance. Right? So I can draw that in anywhere I want, really. Right? I need a perpendicular segment from the top to the bottom. I'm just going to go from point B. I like to go from a vertex, but there's one example of the height. All right, the height is a vertical segment. So if I'm looking at a vertical segment, I'm looking at the y coordinates. So I have a y coordinate of 2, which is good. But then I look down here and I don't know where I have a y coordinate. But look at all the points on this line. Don't all the points on this line have y coordinate -13? So even though I don't know where it hits in terms of x coordinates, if it's on this horizontal segment, its y coordinate is -13. So that height is going to be top minus bottom, which is -13. That's going to be 15. So 9 times 15 makes my area 135. So again, the horizontal one is more obvious, but you have to remember on that vertical segment, you know that any of these y values down here are going to be -13. Any of these y values are going to be 2. So 2 minus -13 gives you that vertical distance. Okay. All right, couple more examples here. We're going to talk about three-dimensional distances. So for those of you who are spatially challenged, I apologize. It says find the interior diagonal of a box whose base has coordinates, and then I give you some points there. So let's sketch a three-dimensional. All right, if you've forgotten, this is x, this is y, and this is z. All right, so 0, 0, 0 is right here. All right, and then 5, 0, 0, so I'd go 5 on the x, 0 on the y, and 0 on the z. 5, 6, 0, so I go 5 here. Now remember, I can't just count out 6 this way. I have to keep it in perspective. So 6 from this point would land me here. But I'm moving 6 from here. So in the perspective, 1, 2, 3, 4, 5, 6 puts me about here for that second point. So this point is the 5, 6, 0. This point is the 5, 0, 0. And then my last point is 0, 6, 0. So that's just 6 on the y, which is right here, and 0 everywhere else. So you can see I've got the base of this box here on that bottom plane. All right, so it says find the interior diagonal whose base is right here, and the box has height 10. So from each one of these, I'm going to draw a segment that's 10. And I'm going to make sure I draw the same height segment, so I'm kind of keeping it in perspective here. All right, so there is my box with this base where they gave me the coordinates, and then this red height of 10. I want an interior diagonal of a box. So I'm going to help you picture that here. Interior diagonal. Let's pick the easiest point to work with, 0, 0, 0. Right, so that's in the back left corner. I'm going to go opposite the box, so back left to top right up here. So if you can picture that diagonal cutting through the middle of that box, that's the one I need to calculate. Well, easy enough. I know this point is 0, 0, 0. The question is, what is this point right here? Well, I went 5 on the x, 6 on the y, but then I went up 10, So that is my z coordinate. So that point is 5, 6, 10. Again, to get to this point, I went 5 on the x, 6 on the y, 10 up, that's the z value. Now that I have these 2 points, I can just use my three-dimensional distance formula. And it's x minus x quantity squared, y minus y quantity squared, z minus z quantity squared. So that's 25 plus 36 plus 100. That comes out to be the square root of 161. And finally, calculate a point that is a fractional part of the distance between 2 points. So I gave you that formula. All right, if you want to look back, we can bring it up here again. So let's refresh quick. All right, here it was. If we have the distance between 2 points, we're going to find the x coordinates. We're going to pick the starting x value, and then we're going to add on a fraction of the distance between the x's. And to get the y coordinate, we take the starting y value and add a fraction of the y distance. So let's look at what that means in terms of our problem. Find the point that is 2/3 of the distance from to -6. So this is my starting point. And 2/3 of the distance, there is my fraction. Okay. So to get my x coordinate, I'm going to pick the starting x value 2, and I'm going to add on a fraction of the x distance. Now remember this x distance right here, that's x2 minus x1. x2 is 11 minus x1. So 11 minus 2, that's like right minus left, represents that distance. So that's 2 plus 2/3 of 9. Well, 3 goes into 9 3 times, so that's 2 plus 6. So that x coordinate comes out to be 8. To get my y value, I take the starting y value, -6, and I add on 2/3 of the y distance, which is y2 minus y1. So my y2 is -3, my y1 is -6. Watch signs, -3 minus -6, that's a plus. So that is -6 plus 2/3 of that distance. -3 plus 6 is 3. Those 3's will cancel. That's -6 plus 2, which is -4. So my point, that is 2/3 of the way from 2, -6 to 11, -3, is the point 8, -4.